Okay, so number 7 and 8 represent questions about mini-tabs. These are just outputs from a type of statistical software that can output different things. In this case, what's outputted in 7 and 8 are confidence intervals. They're actually both 95% confidence intervals. So while I explain this one, I'll kind of go through the parts of this mini-tab output. So the first piece of information we're given is it presents a 95% confidence interval. The assumed sigma, when we see assumed sigma, that refers to the population standard deviation. Sigma is 7.9095. The variable is x. N is, of course, the sample size. Mean, this mean here is our sample mean. This is information based on, this information here is based on a sample, right? The sample size is 35. The sample mean, x bar, is 37.716. And the standard error of the mean, is that sigma over the square root of n piece that we see from our formula. If I go to chapter 7, C confidence interval, T confidence interval, this sigma over the square root of n, that's the standard error of the mean there, or S over the square root of n. That's our standard error of the mean. So, and then we have the actual 95% confidence interval, the left bound and the right bound. Okay, so use the appropriate critical value along with this information in the computer output to construct a 99% confidence interval. Now both of these, since we both have the assumed sigma, we both have the population standard deviation. That means we're using a Z confidence interval because we have sigma. If we didn't have sigma, you just wouldn't see it in that output. We would use the T confidence interval. Okay, so here we go. Here's the Z confidence interval. Let's write it out. X bar minus Z alpha over 2 times the standard error of the mean. That's the left bound. And then the right bound is just X bar plus the Z alpha over 2 value times sigma divided by the square root of n. So if you notice, we have a lot of information, right? We have X bar, that's 37.716. We do not have the Z alpha over 2, but we do have that standard error, 1.3369. You can confirm that by doing 7.90. Well, let's confirm it. 7.99095. That's sigma divided by the square root of n, the square root of 35. And that should be 1.3369, which it is. So this saves us from having to do that calculation, right? To having to do this calculation. But we need to figure out Z alpha over 2. That's like the last piece of information we need in order to be able to do this thing. So let's see. So we want the 99% confidence interval, right? And if you remember confidence intervals, they're two-tailed. They have this kind of feel. So that 99% confidence interval means 99% is in between here. And these two tails have to add up to what's left, to 1%. So each of these is 0.5 of half of a percent. Or if you're strictly using decimals, is 0.005, right? 0.005. Now, if you're doing this using the longer approach to determine what the critical value, what this value here is, that's our critical value here. To determine what these values are, you can go to the table, to the Z distribution table, which gives us the area to the left of a particular Z value, and find 0.005, whoops, sorry, wrong place, and go down to the z distribution table, and find as close as we can get to 0.005 in here, and it'll probably be between these two values, 0.005. So negative 2.58 if we're rounding, right? That's the longer way to do this. The quick and dirty way to do it, right, is realize that we have a 99% confidence interval, and go all the way down to the t-distribution. Confidence interval, 99%, right? 99%. And go all the way to the bottom, and it gives you the z value that you need. 2.576 or 2.58 if we round, which is exactly what we have gotten the other way. So the quick way, go down to the t-distribution, regardless of if you're using z or t. For the confidence intervals, go straight down to the t-distribution. Find the confidence interval that we're looking for, that we're interested in, 99%. And all the way down to the bottom, 2.58. So that's actually our critical value there. 2.58, negative 2.58. And that's what goes in here. And on the other side, 37.716 plus 2.58 times 1.3369. Now what I'm showing you is how to construct the entire confidence interval. You do this calculation, you do this calculation, and you'll get the bounds for a 99% confidence interval. But the answer to the question, oh, we're actually constructing it. Yes. I thought they just wanted the critical values. So let's actually do it. 37.716 minus 2.58 times 1.3369. 34.266 or 267. 34.267. That's the lower bound. And let's just press second enter and go back and change that minus to plus. That's all we need to do. 41.165. And that's our answer. That's the 99% confidence interval. So in words, this means that we're 99% confident that the true population mean is between 34.267 and 41.165. We're 95% confident that it's between these two values. And notice, if we want to be more confident, the interval has to be wider, right? It goes down to 34.267 and up to 41.165. If we want to be more sure, more confident, we make that confidence interval wider. Okay, next problem. Again, this is a Minitab output, 95% confidence interval, sigma, population standard deviation, 12.1675. And we have a 60 item sample. Sample mean here, x bar. Standard error of the mean, etc., etc. Now this problem is asking us to find the sample size needed so that this 99% confidence interval will have a 1.4 margin of error. The margin of error is this here. It's the sample mean minus the margin of error, sample mean plus the margin of error. So this here, the standard error of the mean times the critical value, that's our margin of error. But there's a formula for this, for finding the sample size needed to get a certain confidence interval and a certain margin of error. Chapter 7 is what I'm looking at. Here we go. Sample size for means. This is the sample size that we need, and E is the maximum error of the estimate, also known as the margin of error. All right, so Z alpha over 2 times sigma over E squared. Let's see, alpha over 2 times sigma over E squared. And we have all of this information, right? The 99% confidence interval is where we get that Z alpha over 2 value from. And we found that in the last problem. That Z alpha over 2 is 2.58 for a 99% confidence interval. Times sigma times 12.1675 divided by the margin of error, which we're given as 1.4. And all this is being squared. I'm going to throw this right into the calculator. So let's open parentheses, 2.58 times 12.1675 divided by 1.4. The calculator is going to do that in the order it appears. So, and then let's square that. 502.8. Now this is the size the sample needs to be so that the 99% confidence interval has that margin of error. But can't have 502.8 people, things, items in my sample. So we need to always round up, because 503 would automatically ensure that I have that 502.8 in there. So just round up. Round to the nearest unit, I should say. So 503 is the sample size we need. Now, if you notice, the multiple choice, or the answer on the answer sheet says 502. I'll tell you why that is. Let me tell you why that is. Okay, so when I go to the table to get the 99% confidence interval, that value is actually 2.576, right? But we round up to 2.58 just to get those two decimal places. But it's actually 2.576 if it's unrounded. As you can see here, it says this value has been rounded to 2.58 in the textbook, but it's 2.576. If I do this problem and use 2.576 as my Z alpha over 2, times 12.1675 divided by 1.4, and then square that, I get 501.23, which rounds up to 502. So that's the discrepancy by that in that unit. If you round to 2.58, you'll get 503. If you use 2.576, you'll round to 502. So that's the discrepancy there.